Ladies and gentlemen, dear friends and guests of KTI, a very warm welcome to the first event of KTI during the Expo. The Expo is probably the best ever world exhibition. When you walk through the pavilions, you'll find the subject is mobility, opportunity and sustainability. Actually, sustainability is the subject for all of us in the future, for our future, for the future of the children and the grandchildren. To be honest, we are here since 35 years, and a humble remark is that we probably contributed a lot to the sustainability here in the Middle East. Without the cooling of the concrete, you would not be able to have all these buildings. It's not all to blame KTI, but at least 90% of the buildings here have been cooled with KTI equipment. You must imagine about 500 million cubic meters of concrete have been the last 20, 30 years produced. That means roughly 50 million cubic meters of water, and for sure 20 to 30 million tons of ice have been used to build up this environment in the Emirates, Qatar as well, Saudi Arabia. I don't have the figures for these countries, but I think we can be proud what we have achieved. And it's a necessity that we improve what we are doing. In the last 10 years, energy costs money here, almost as much as in Germany. 15 years ago, you asked about economic operation of a plane, say, Hali, we are not paying anything or not much, but now it's different, and we have to pay. Everybody has to pay what he is using. So we have, since 5 or 10 years now, developed concrete cooling system where you can save up to 50% in the power consumption. That's a lot. I mean, today I was talking to Dubai Ready Mix, and they are using 1.5 million in electricity just for the refrigeration equipment. If you can cut it down to 700,000, you save a lot. Now we're talking about hundreds of ready mix plants which are running here. But we are not talking so much. Could you understand so far? Do I have to repeat everything? Sorry, I go closer now. But we are not here to talk about the ice and what we did in the past or what we intend to do. There's much more about sustainability in the concrete and in the construction business. When you talk to the local government people, they are now coming up with the green cement, whatever that is, but everybody thinks about how can we save energy to save the planet. And therefore I have invited Mr. Gerdes, Professor Gerdes from the University Karlsruhe Institute of Technology, and he's the director there. And whenever he talks to me and to others, you see how excited he is and how much more is possible in the future and necessary. So I don't want to bore you with some theoretical stuff. I give now the word to Professor Gerdes. The stage is yours.
Thank you, Mr. Plesch, and I think it's a really great honor for me to be here and to give a lecture about our research work, but not only about our research work in Karlsruhe, but also the practical applications of our results in basic research. And this is a very important point, how we can transfer these basic research very fast in our economy, because this is an important precondition to make steps forward in sustainability. That's one of the preconditions. And I will give you a lecture because our topic is infrastructure, which deals with the challenges but also the opportunities in the field of infrastructure in the world. because everybody knows in this room, I'm sure, without a strong infrastructure, we will not have a strong economy. That's really important. So now I get my second tool. I would like also to say hello to old friends. I know already for a longer time, and I hope for new friends. And for new friends, I will find this evening, because we try to make more discussions in all other parts of the world. And this is my first presentation of these results outside of Germany. But we have already introduced it in the technical market in our land. So, and I will start with an example which shows clearly how durable cement-based, mineral-based materials can be. And I will show you some infrastructure from the past. And this is an investigation we have done with archaeologists some years ago, and we investigated several cisterns in the region of the Mediterranean Sea, which are all 2,000 years old and older. And I look television, and I saw my colleague, an archaeologist from Tübingen, and he presented this cisterns and told us they are working still for 2,000 years. And I say, unbelievable. What is the reason for that? But we know often these structures worked only for 10 years, made with the modernest materials we can use. And this worked for 2,000 years. What are the reasons? What can we learn from these experiences in the past? And for that, we take course on the Acropolis on Pantelleria. You can see 43 ancient cisterns, and they were made by the Phoenicians. They developed this technology, I will show, and the Romans copied it later. And if we have a look to the cisterns, you can see here there's an excavation in this rock, and then, because this is a porous rock, it's necessary to put a mortar on the surface to prevent the outflow of the water. And now, please look to the left side, and you can see there are 3 layers. And it's interesting to learn the first one is made by the Phoenicians 2,000 years ago. The second one is also made by the Phoenicians, but it's a development. And if you have a look on it, I talked already with some of you this last days and this afternoon. This is made using fly ash. So this is not a new result of research. 2,000 years ago already, these raw materials are used, not ordinary Portland cement as one component, but lime and the fly ashes. And these materials are so durable that it works until today. And this is the technology made by the Romans. They had no idea at this time that it's possible to use fly ashes, volcanic ashes. Therefore, they have transported from Sicilia to Pantelleria, a distance of 180 kilometers, these ceramic materials in order to create a mortar. But they had no idea that they can use the volcanic ash on the island, which is only 500 meters away from the Acropolis. And that's what we are calling technology transfer in ancient times. And they did it already because we found around the Mediterranean Sea everywhere this technology. And this is one of our greatest tasks, your task, my task, that we are talking together, communicating and creating technology transfer in both directions. This is really an important task for our daily work. So, and here we visited this cistern after 2,000 years the first time, and it looks as it was made a day before. Therefore, and this is a message of these experiences, it is possible to build durable using materials like concrete. We can do it. And we can do it for a very, very long period if we know how it works and how to do it. Fortunately, a lot of experts in this room who know it, how we have to do it, but we have to show, especially the customers, that it's necessary to use perfect concrete, high-performance concrete with a high quality. Otherwise, it will not work and it will not survive 100 years. It will not survive 10 years. So now you remember it's a secret. I have seen the movie and the television. I have no idea how it works, and therefore I'm a researcher, I'm a scientist. I try to clear up what is the reason for this high durability, and I will tell you the secret. We have a multi-layer structure. A first layer with a porous mineral-based mortar made with ceramic aggregates. And then on the first layer, a very thin layer is put on it. You can see it here. And this is like a polish coat as finished on this first porous coating layer. And that leads, you can see it. This is a core from this material, the porous material, and the polished, finished. And we have tested the performance of this material. We have measured the water uptake coefficient, because you know if a material is porous, then easily materials can go out. They migrate from the mortar into the drinking water, or vice versa, and that will lead finally to a leaching which reduces the service life. And therefore we have tested the water uptake of the porous material, blue colored, so it's a high water uptake, but this polished coat, there's a low uptake. And this is the solution, that's the reason for the high durability. Because if you have a new cement-based material like a mortar or concrete, you will have this layer or this part of our concrete will be porous, so we have there a high water uptake, and the rest of the concrete we will have a low water uptake. So it's quite the opposite compared to the old system. But this is the reason for the high durability, because due to the dense pore structure, there's only a low transport of calcium out into the drinking water, and this what is lost can be transported in the covercrete, and therefore we can stabilize this very thin layer, and that leads to the high durability. So what we have done in cooperation with a small company, we developed this system with new raw materials, and now it's one of the best water reservoir coatings in Germany, because the durability is comparable with the durability of these systems. Only due to the opposite porosity profile. That's the reason for that. Very simple. So now we have learned already that cement-based materials are porous. And we are often talking in our business about strength. This is the most important factor. But this is not really important for durability, the strength. There are other factors we have to take into account. And unfortunately, we are making all a great job, because it's really complex to create or to make a high-performance concrete. It's not so simple. But it looks simple. This is a major problem in our business. We have aggregates, we have cement, water admixture. We are mixing that, the hydration of cement started, and then we will get this complex composite material. However, so far we are not really known all chemical reaction taking place during the hydration of the cements. But these hydration reactions determine the performance of the concrete because type and amount of raw materials used like these will influence the composition of this material. And the boundary condition like hydration or the construction phase will also influence the performance of this material. But it's important to know the durability depends on the pore structure and the chemical reactivity. So what we have done some years ago, we use cement, put it in a chemical reactor and produce organic compounds in a better way than a classical chemical process. Because this cement works in two ways. First, it collected the water, and second, we have a high pH. And so we get a better result at the end of this technical process compared to classical approaches. So you can use cement for a lot of different things, but you have to into account pore structure and the chemical reactivity is decisive for the performance and finally for the durability of the structures. Here are some figures about the structure of the cement. And if we have a look in the pore structure, we can see there are a lot of pores with different diameters. So we have not one pore with one diameter, we have a pore size distribution. And this, you can see here, are the hydration products. It's like art. It's like really a nice, let me say, a nice result of our nature to show us these fine needles which forms the CSH gel, which is a binding component in the concrete. And it's nice also to know, I think, for Mrs. Blairsch and Mr. Blairsch, this is strongly influenced by the temperature. If you have higher temperatures, these needles will be shorter than at lower temperatures. And that's had a strong influence on the performance of the concrete. So it's not only necessary to reduce the temperature for the workability or to prevent the formation of cracks. No, it's also important for the quality of the concrete itself. And if we have a look on the next, these are 200 nanometers magnification. And this is the cement-based material I have shown on the figures before. And if you compare it to that, this is a boon. So that means the porous structure of a boon is very similar to the porous structure of our cement-based material. And that's the reason why we have to take into account to have care not to damage the boons of our concrete structures. And that can be a result. You can see here, this is a serious problem. I'm sure you know this chemical reaction. It's called alkali-silica reaction, and this alkali-silica reaction leads to the complete damage of the cement-based material, forming these cracks. And this is, for example, a serious problem of most of all airports around the world. And this depends not on the strength. It depends on the nanostructure and chemical reactivity of our hardened cement paste. And both depends on the concrete composition and this is the most important point, on the workmanship. Because if you prepare the perfect concrete, but there's nobody on the construction side who can apply this material in the right way, then of course the best concrete in the world doesn't work. So therefore it's necessary not only to control the concrete, but also to control the ready construction, making a quality control. Please remember, we are paying sometimes millions of dollars for one construction. But if you ask the planner how much money you will spend for quality control, no money, $0. And will you accept a car without any control, quality control? Never will accept it. And your cars are expensive, I know, I see these cars. But they are not so expensive as your constructions in Dubai and in the United Arab Emirates. Therefore, quality control on the construction side is the easiest and the cheapest way to save money and to extend the service life. And that's what we have to establish in our business as fast as possible. But this is not a job for a civil engineer, unfortunately. This is a job for material scientists or chemists who are familiar with this reaction taking place during the hydration, and they will be able to characterize reactions which are harmful for these structures. So now we have to prevent it. We did it. This is the airport of Leipzig, the biggest airport in Germany. I know you will be surprised. Frankfurt should be the biggest one. No, this airport is bigger, but nobody traveled to this airport because this is the hub of DHL, the International Parcel Transport Company. And what did we? We treated the surface of the structure with a silicon organic compound, 120,000 square meters. The price is approximately $10 per square meter, and we stopped the alkali silica reaction. This is a good investment, and we call it prevention in construction. We should not wait until the structure is damaged. We have to do something before. Well, that means during the first 20-25 years, because normally the damages occur after this time, we should not wait until these demolitions occur. We can do something, and it's very simple. We put, for example, in this case, a liquid on the surface, and that will protect this structure for minimum 25 years. And after that, we can do it again without any restrictions. So it works very well. Infrastructure modern times. My wife was so nice to give me this picture. And you know, this is the skyline of Dubai, and you can see a lot of infrastructure. Okay, we are talking about residences, we are talking about hotels, but in fact, it's infrastructure for the tourists, for other people, and this infrastructure is connected to more infrastructure. Therefore, our first goal must be to protect our infrastructure in modern times. And now I will give you some numbers. These numbers are given by the McKinsey consulting company. They made a really interesting study some years ago, and therefore, in the time from 2013 to 2030, 40 trillion euros will be invested worldwide in infrastructure. This is the biggest market in the world, period. That means every year, $4 to $5 trillion investment. Do we have an idea about the investment in the automotive industry? More or less than 4 trillion euros or dollars? It's only $1 trillion. So that means the construction sector, the investment in the infrastructure is 4 to 5 times higher compared to the worldwide automotive industry. This will be our business in the next decades around the world. This is a bad number. We have to change something. And I have a nice talk with one of my colleagues from Germany. He lived near to my hometown in Germany. And he's talking about digitalization in the construction sector. This is also a number of McKinsey. The improving in labor productivity over the last 20 years in Japan, Germany, and in the United States was 0%. We are working the last 20 years in the same way. But the prices increases. In this way, it's not possible to earn money in the future. We have to change, we have to do a lot of things to modernize the construction sector. And this is not only the material, it's also the digitalization. This is an information for you. 80% of German companies in the main construction sector have fewer than 20 employees. So a lot of construction sectors worldwide are, let me say, dominated by small and middle enterprises. So huge companies like here we had in Germany so far. But how we can deal with this complex system infrastructure? We did it in the following way. We organized this huge market and say mobility, that means roads or bridges, urban infrastructure, very important, like schools or hospitals, information. Okay, we have all our cell phone, 4G, 5G, but we need also infrastructure. Industrial infrastructure, for example, if Sheikh Tazir invests a lot of money in their production line, he will not be happy if after 7 years that construction damaged or collapsed. Therefore, it's necessary to extend their level. Water supply and sewage water plants, and finally, of course, energy. These are the different parts of infrastructure, and there is one point which is common for all these, and this is concrete. Because for all erection of these structures, it's necessary to have a good concrete and to prepare with this concrete our structures. So now, how we can extend the service life? And this is what we call prevention in construction. I will show you later some activities, how you can do it in practice. And we can extend the service life for 4 times. And the price for that is approximately 3 to 5% of the initial construction costs. So you will not pay 100%, you will pay 104%, and then you will get not 25 years, but you will get 100 years service life. That's a good business, isn't it? Yeah. Because we can reduce drastically the service life costs. And this is not only one advantage of this strategy, because we can also reduce the environmental impact, we can improve the CO2 footprint of our structure, very simple and very soon. Because this is our work, what we will done in Karlsruhe in our research and development work, because the sustainable development goals means sustainable infrastructure. We can't do it without this infrastructure, because clean energy, impossible without infrastructure. Industry innovation and infrastructure, there's already named this point. Sustainable cities and communities, impossible without durable infrastructure. Clean water and sanitation. These are all goals of the United Nations, and we can only reach it with a high-performance infrastructure. However, we face already a lot of problems in this business. And the first problem is climate change. I show you the airport of Leipzig, and this is really a huge airport, so that we have 700 kilometers joints on this airport. And every year, 100 kilometers must be repaired, due to the fact that these materials are not made for the higher temperature in Germany. So, a simple solution, we will use the material used in Dubai. But it doesn't work because we have also cold winters in Germany. So we can observe that the interval of temperature become wider and wider, and therefore we need new materials for this application. Resources, lack of resources. Everybody knows it's not so easy to get good aggregates, good gravels and sand. Sand become more and more expensive, and therefore we have to look to replace it. One way can be, for example, using recycling materials or recycling concrete. The other way, we are working on it, why we can use the sand from the desert. And the way we add some additives which lead to a better adhesion between the single sand corns. Thank you very much for sending the sand to us for testing. Megacities. The cities become bigger and bigger, and that means we have a difficult combination of different infrastructure, globalization, and finally digitalization. All this leads to this situation, damaged infrastructure. So that we can say the reasons for the bad current state is insufficient quality of construction materials, inadequate planning and execution. Why? Our standards and rules are made for 20 or 30 years. Very old. Will you buy a cell phone which was made 30 years ago? No, no, definitely no. Nobody wants a 30 years old cell phone. But we did it in the same way with our structures. The technology is 30, 40 years old. So that means the regulations and standards stops innovations in the construction sector. Because this is a look in the history, not a look in the future. Therefore, we have to change our strategies to develop new building materials and admixtures. Shift in usage. Sometimes the construction is used, for example, as a hotel and later as a lab. And of course, the change of environmental impacts. That means we need new innovations in the construction sector. But this is not the simple solution. It's not enough to prepare to create a new cement or to create a new concrete. What we have to do is to create a new service life of these structures, including quality control, recycling measures, surface protection systems, and so on. Because our job is not to prepare the building materials, our job is to prepare durable structures for our customers. So you can see I'm not a typical professor, I'm also talking about business, not only about research. So that means we need, these are essential. And that's what we are doing in the KIT Innovation Hub in Karlsruhe. This is the Institute of Functional Interfaces, our working rooms, in which we are sitting together with all stakeholders along the supply chain, beginning from raw materials supplier like BASF or other huge chemical companies, cement producers, concrete producers, up to the public owner. And we are sitting around the table now talking about what will happen in the near future. What we have, what are our challenge? We have to do it together. We have to talk in one group to identify these problems. And that's what we are doing here with a team of approximately 20 experts working in this field. you're all invited to come to us and to visit us if you're interested. So, because what happened right now in the construction sector? We have a huge transformation in the construction sector in Europe right now. And this is what we are, let me say, realize right now. These steps are the so-called technology readiness level developed many years ago by the NASA. And it shows starting from the idea, making a prototype, validation, and finally the production. And what we are doing in our sector is here and here. But we need these steps between these both, idea and application. And then we will be able for a technology transfer, which is very fast and very, let me say, successful. That's what we have introduced into the construction market. We started at basic research, applied research, and the technology transfer into the market. And that's how we do it. We are doing basic research at the KIT, applied research at the University of Applied Science, and in a company I founded some years ago, we started to transfer these ideas, these products to practice. And the basic idea is to parallelize this project, because today we have on one location the basic group research, the applied group research, and there the technology transfer experts. But they never talk with each other, and there it's difficult to make the technology transfer. In my group, I have 3 groups in the company in order to collaborate with each of the other groups. So in this way, we can parallelize the technology development process and reduce the process from the time to the half. We accelerate this process, and we got very strong patents. So normally you need 10 years, we need 4 years, some cases only 1 year to create new products. And the next step is the innovation apprehension and construction to transfer and to disseminate these results to the public owner. We are doing consultancy and information. But this is located at a university. This is not located in a company. It's a company and a university branch at the same time. This is the basic idea. And what we are doing, we are foresight innovation communities. I mentioned it already. We're sitting together and we are looking to see future things. We manage new things in order to translate technical results into economical or economic processes. We are sharing with each colleagues around the world because the idea is to translate these problems in solutions. We are communicating these to the relevant groups. And of course, we teach our students in this way to become better engineers after their study and to learn something, how they can protect our environment. And therefore, we have developed our own, let me say, our own innovation process, which leads to the product and to the knowledge, because both is necessary for our customers and means the public owner to create sustainable infrastructure. We need both. So, and this is the basic idea, increasing the real service life of 20 to 30 years for new structures, but also for already existing structures, because this is very important. To wait until these structures collapsed and then we build a sustainable structure, it makes no sense. We have to wait 30 years. But in this way, we can do it also with already existing structures to extend the service life. And there are a lot of different tools we have developed during the last 10 years. So, and I will show you now some examples for that. Innovations and projects. First of all, we need new strategies. Most of all developments in our business are empirical. We prepare 100 mixes, we test these mixes, and then we were satisfied or disappointed. Therefore, we have to do it in the same way as, for example, the pharmaceutical industry do it already for years, using high-tech tools like computer software, so on. I will show it to you. This is, for example, the strategy in pharmacy, the target identification. This is the action of mRNA drug for the vaccination against COVID. Then we are searching for suitable active agent molecules. We are just built out special types of robots which will prepare one mix, and in the next step they will test it. So we are very fast to test our best ideas about new admixtures, for example. But it's very important computational chemistry in the drug development to create these molecules and to learn how we have to create the drugs. And so on and so on. This is a clear strategy. So when we transferred it to the construction sector, we are working like a pharmaceutical industry to create new additives. That's the basic idea. But we have not to characterize the biomolecules in our body. We have to characterize mineral surfaces using high sophisticated tools. I mentioned it already. We are using robots for the investigation of new mixtures. Then we are using computational chemistry to optimize, for example, the molecule of a superplasticizer, to improve the performance or to reduce the products. Performance, formulation. So this is a similar process for the transfer of basic research results to the praxis. And there's a short overview about the technologies we use for that. These are all high sophisticated analytical tools, starting from the molecular level up to the construction site. This is the basic idea, ever. And this is the selected methods for modeling, ab initio methods, density, functional theory, and so on. We are using these software tools to get the information about the interactions between the chemical admixtures for the concrete and the mineral-based systems. Now you are thinking, this is basic research. I can never sold these products because I have to wait 25 years for the result. No, not true. I will show you one of the results of this work. This is a development of the company, Gerdes, and this is an inhibitor for the prevention of alkali silica reaction. This powder is a complex combination of a mineral carrier material, an active component which prevent the 𝐕𝐳𝐴 reaction, and a coupling agent. And in this way, we put the active agent on this surface of this mineral powder, and then we will add this powder to dry mix systems. For example, cement or other cement-based mixes, dry mixes. And then we added water, and then you can see in a determined process, these substances are liberated, and the mineral substance will working like microsilica, because it's a type of microsilica. So we have two actions, the action of the microsilica and the prevention of the 𝐕𝐳𝐴 reaction. And it works. You can see here, these results are made by the Federal Materials Testing Institute of Germany. Here you can see this is a test at 60 degrees in an alkaline environment according to the rules. And this is the concrete the strain in millimeter per meter as a function of time for the untreated concrete with 5% sodium chloride, 3% sodium chloride, and with 10% sodium chloride. And now you can see the application of this DMX, this additive. There's no strain compared to this. And you have to add only 0.7% related to the cement weight. That's nothing. It's nothing from the weight, and it's also nothing from the money. But it leads to a high resistance against these reactions. And if I come back to the use of recycling materials in concrete, we can only use these recycling materials if this is contaminated, if we add something like that. And this is the result of our work I showed before. And we need 1 year for the development of this product. And it's unique in its performance and in its application. So, this I mentioned already. I will come to the end. This is already the protection of the concrete of this airfields against RSR using hydrophobic silane-based agent to prevent the absorption of aqueous solution of the de-icing agents. We did it some years ago, and it works very well up to now. And I think it will work for the next 20 years. Then we have to redo it. Drinking water reservoirs. This is, of course, crucial for each human being to have enough clear and good water. But it's very important to store this water, and therefore it's necessary to create new inner surfaces. I know that the British colleagues using epoxy resin for the protection of concrete in tapewater reservoirs. In Germany, it's forbidden. It's not allowed because the risk is too high that biofilms are formed of the inner surface and will ruin the water. Therefore, it's not allowed. We are also using cement-based materials, mortars, and made like the Phoenicians and Romans 2,000 years ago. That's our technology. And it's better to use these cement-based mortars, ready-mix mortars, sent to the construction site, applied there, and it works for decades without any problem. But using polymers is really a high risk for the water quality. I work already for 30 years in this business, and I have seen everything in this context. And this is our next step, and I'm very proud about it, because I convinced the mayor of the city of Leutkirch in Germany to change their strategy. Up to now, they are thinking we will plan our structures based on the construction costs. Now we will change in the next 5 years the whole infrastructure to planning based on life cycle costs. That will be the first city in Germany and maybe the first city in the world where we are doing all infrastructure will only built and planned on the service life costs, the life cycle costs, not on the construction costs. And not only the financial costs, but also the ecological costs and the technical costs. This is another project we did for the German government because we have developed a cross-modal, so for the railway, waterways, and for the highways, one concept to get an environmental, compatible, and resilient design of transport infrastructure. And this is, let me say, more or less a software approach we have developed for that, so that we can manage in a life cycle management concept this type of infrastructure with one rule, with one standard. So up to date, we have 3 standards for all, but it makes no sense. Why? In all cases, we are using concrete. And the concrete is the most important factor for the durability and performance of these structures. So then I will come to the end of my presentation and to my conclusions. I think first, the consequences of megatrends, such as climate change, will also place higher demand on cement-based materials in respect of performance and durability. And that will be our job to do it for our customers. It's hard work, but we have to do it. The restoration-free service life of structures can be extended in a efficient way by the application of preventive measures during the service life, which also leads to a significant reduction in economic and ecological burdens. This is a change in mind. For that is necessary, not a change in our tools. We have already these tools. And this is another point. In the construction sector, we are talking about the next day. And the next day, we were talking about the next day. Unbelievable. We are constructing infrastructure for a service life of 100 years. So we have today taking into account what will happen during the next decades in our plans and activities. Therefore, we need foresight processes. Your new car is already planned in Stuttgart, Daimler-Benz. They are now thinking about what will be interesting for you to have in your car in 10 years. Now, this moment. And we are not thinking about what will happen in 20 years with our structure. So we have to do the same job as the automotive industry. And we need new offers for the education. So we have a lot of civil engineers in our business, good economists in our business, but we need also good material scientists in our business, chemists, and so on. This is really rare. So I'm ever looking for a colleague who is also a chemist. It's not often the case that I find someone. And this is very important, we need new formats to talk with each other. We are partners in the construction world, and for a durable construction, we need communication, starting from the raw material supplier up to the public owner. Otherwise, we will not be able to create a durable construction. Thank you very much for your attention. I hope I can show what we can do in the future, and will a pleasure for me to discuss after the presentation with you about your ideas. I'm really curious about it. Thank you very much. Of course, we have the opportunity, I think a pleasure for questions. He will overtake the management. So.
Well, I could listen to you longer than these 45 minutes now. I was hoping you speak for maybe half an hour more, because you have so much experience in your lifetime, and I think we all should be grateful to share this knowledge. In my person, I was only looking concrete and ice and cooling, but there's so much more to get it involved. I mean, you see yourself, probably he might have told you a few things but you didn't know yet. So it's a fascinating job, and I wish I could stay in the business a little bit longer than 10 years, but I think sooner or later you have to get out. Nevertheless, if somebody has a question or comment, it's highly recommended. I ask you to just give some comments, whatever, yeah? If you give some comments, maybe you have some doubts or some questions.
So it would be better, check that if you use a microphone, then everybody can hear you.
By adding additives to the cement, to what extent we can increase the time life?
So, for example, if you use this type I show you as a new development, we can extend it from maybe 10 years, 15 years to 60 to 70 years. If we use, for example, the water repellent treatment for harbors, because there we have a high impact of chlorides, we can extend it to 100 years. And normally after 15 years, you have a lot of concrete damages and you have to repair it. So it depends on the grade of or severeness of the impact. But I think that's our idea. We can extend it in all cases to 100 years to the plant if we are taking into account this process at the beginning of the planning. So it's a special type, you know, you have a concrete consultant and so on, but we need also a durability consultant who tells the planners what is to do to get the best, and that's these admixtures.
Up to what extent the rules are matured in Europe, for example, to ask for guarantees up to 60 years, or to make like this new city as an example that based on the life cycle, it's the opposite approach. So up to what extent now the rules are matured?
So first of all, the guarantee in Germany for a new construction is 5 years. That's nothing compared to a planned service life of 100. That means, for example, for a watch, 6 weeks guarantee. You know, it makes no sense. On the other hand, all of these things we have developed follows the rules. So we are not working against the rules. There's enough space in the rules to realize it without any trouble. And that was the reason why it's so simple to convince the public owners to change their strategy, to change their working. Because they are not in trouble, because they are using not longer the standards and rules.
So I think there is a lot of, there is an intensive work should be taken with the stakeholders to develop the rules to be matured enough with these technologies. Yeah.
You are right, but you spend sometimes 10 to 15 years to modify the rules, and that is our major problem. And that was the reason why I have my personal strategy changed 5, 6 years ago. Now I never talk with a planner, I never talk with a construction company. Only one person is interested in a long service life, the public owner. And therefore I go directly to the public owner, sitting together and show him, look, it is possible. And I have learned in Germany, a lot of mayors are really in trouble because they are open the school way apart. And 6 years later, there's a big article in the newspaper, a lot of damages, and then he will be not the best man, he was the worst man in this case. Therefore, it's necessary to talk with guys because they are interested to make the situation better for several reasons. Yeah. Yes, sure, you can. Yeah. I will give the presentation to Mr. Plesch, and he will put it on the homepage of KTI. I think it's a simple base, then you can download it without any problem. Yeah, sure.
Yeah, excuse me, you mentioned some chemical to be sprayed on the concrete.
Yeah.
Okay, definitely there is some repair required for the existing concrete before applying this spray.
Yeah.
And what about the reinforcement which is inside?
Okay. Yeah.
Please.
So we called it a silent-based impregnation. And the silent-based impregnation is a silicon organic compound which penetrates into the concrete. And if you use the right material, the penetration depth is around 5-6 millimeters. And that means the covercrete protects your impregnation and therefore your surface protection system. And if this is an old concrete, if it's a dirt concrete, doesn't matter, because this is a liquid, a low viscous liquid, which can penetrate into the covercrete. So therefore, if there's already, for example, a chloride contamination, you can do it. We did it in Germany. You know, in Germany, the highways, we are using de-icing salts during the winter. There's a high penetration depth of the chlorides. And we have a covercrete thickness, maybe 4 centimeters. And if the penetration depth is 3 centimeters of chloride, we apply it and we stop the further chloride transport. We did it with a nude construction, and we treated the whole bridge without an area of 1 or 2 square meters. After 15 years, we investigated the chloride penetration depths, treated and untreated. The penetration depth for the treated surface was 5 millimeters after 15 years. But for the untreated, 560 centimeters after 15 years. So there we are already in trouble because this chloride front is behind the reinforcement. And it can be applied easily. You need only, you can spray it on the surface. The reinforcement is, there's no problem because the penetration depth is only 6 millimeters. And then, of course, there's no interaction with the reinforcement. And if you are lucky, it's not really good. But due to the fact that no longer water penetrates, there's a drop in the water content. And that can be, if there's a dry atmosphere like here, stops the corrosion process. We observed it in practice, but it's not really a scientific-based method to prevent the corrosion. But it helps to stop corrosion processes.
Can you please share with us how will you assess or test the durability for 100 years? Is it using curing chambers with different temperatures? How can you assess it?
So, of course, it's often difficult to make experiments in a laboratory and to get information how long it will work. That's the reason why we're using these high sophisticated tools to build up models, because with these models we can calculate what will happen because we understand the mechanisms. And that will be combined with experiments in the laboratory. For example, which is very powerful but simple, the measurement of the capillary uptake of water, and then we compare it. Or we are using ER spectroscopy to characterize the amount of silence which penetrates into the concrete. We are using, for example, electron microscopy. So there are a lot of tools usually used, but we are thinking about first how we can show the performance of the material and the alteration of the material, and then we start to investigate. And what we're also doing, we go outside looking for old examples like the cisterns on Pantelleria to learn something about the physical and chemical basics of this behavior. And this is our, this is our treasure, to know these interactions and to know what are the important factors which influence the long-term performance.
In the city of Leutkirch, so is there an anticipated impact for the investment cost, but more important also for the savings you do?
So I mentioned it already. The investment at the beginning of the construction or during the use is 1 to 2, maximum 3% of the construction costs. That's nothing. That's really nothing. So it's the best business you can do if you extend the service life in this way. And not only for the financial, but also for ecological reasons. And I think from my point of view, it's very important. We can do it already. We can go outside and we can protect the next bridge on the way from here to the city of Dubai. And this is important because we have to reduce the impact now, not in 20 years with new constructions, better concrete or green cements or something like that. That's too late. We have start today with our already existing infrastructure. And for that, the tools are there.
So from the financial point of view, are we able then to give like a certificate or proof to make the depreciation at 60 years, for example?
So I can do it because I will not live in 60 years, so it's no problem to do it. Huh? No. What we are doing, and this is also important, because after treatment, we make a quality control. I mentioned it already. We have no quality control concepts on in the market. Unbelievable. We are paying hundreds of millions euros for our construction, but nobody will pay $5 for the quality control. That's, sorry, but I come from the northwestern part of Germany. We are telling what we are thinking. And I think that's stupid. That's really stupid. So we can do it. We make the quality control, maybe directly after application. And 10 years later, we do it again. And then we can observe how the performance of this treatment is. And it's good. Okay, we can continue 10 years. And if it's not good, we do it again and protect it again. So that is important to have an observation along the service life. Because up to now, what is the test? So in Germany, every 5 years, the bridges. It's also stupid, because we get only an information about this day. But we don't know if the chloride front is only 1 millimeter or 1 centimeter away from the reinforcement. And this is, in this way, it's not possible to make life cycle management, because we have no idea. We have the idea about the actual state, but not about the near future. And therefore, we need sensors, we need high sophisticated analytical tools, and so on and so on. And then it works. So it's necessary to have care to our structures. Further questions? Because now it's for free. Later, it will change. No, it's a joke, of course. Okay. So I think it will be,
I just want to mention something here, because Professor Gerdes, he only talked about, maybe give 1 or 2 examples about the innovations we have in KIT Innovation Hub. Okay, I think if we start to just have a list of our innovations, I think we'll stay here until tomorrow, okay, for discussions. So I think if anybody interested, okay, to know more about what we have in KIT Innovation Hub, he can contact us. He's welcome to visit us for sure, and we can discuss anything in details with him. So you are welcome at any time in our KIT Innovation Hub. Thank you.
Dr. Hashim is my colleague, and I have paid him for that, to tell that. Okay. If there are no further questions, I say again, thank you.